Okay, and the third part of section 6, it's a long section. I don't know why in the book they put it in one section. We're going to talk about common factors in numerator and denominator, how they are going to affect the graph. Let's consider first example. F of x equals x squared minus 2x divided over, divided over x minus 2, x minus 1. Let's imagine somebody gives us already factor denominator and they're asking graph it. You start looking at this expression and you see that actually from numerator you can factor out x, and that's going to be x minus 2 in parentheses, and over here x minus 2 and x minus 1. So when you factor x minus 2, you can always cancel it. And that's going to be x over x minus 1, which by long division or short division, I don't know, you can do the short division, x minus 1. It's going to give you 1 plus 1, x plus x minus 1. Can be just modified into a normal hyperbola, right? And you can just graph it. You see that it's shifted 1 unit up and 1 unit to the right. Vertical asymptote 1 and 1. 1 here and 1 here. I'm going to write 1 unit up and 1 unit to the right. Now, what was that about x minus 2? Because if you look at this expression, you're going to see that x minus 2 in an original function sits in denominator, so x is not actually equal to 2. How it's going to be reflected on my graph after I graph it finally? Well, this is 2, right? And I understand that at 2, I don't have any value for the function. So what you should do for the picture? On the picture, you're going to put a hole like this, which is going to tell you that function is undefined. And it looks like this one is 1, this one is 1, this one is 2, this point is 2. Okay. So whenever you have same factor in numerator and denominator, you can always cancel it, but don't forget that the number is still not going to be allowed at this point. So x minus 2, for example, you cannot plug in 2 here into original function just because it's having 0 in denominator and it's going to be undefined. On your picture is going to be a hole in the graph. I'll ask you to now kind of do similar calculations. So let's try to do self-work. Y equals 2x squared minus 2x over x squared minus 1. So again, I'm asking you to graph it, and I want you to remember about the possible hole in the graph. Remember that zeros of denominator are going to be undefined for this function. And sometimes they will give you vertical asymptote, and sometimes they will just kind of give you a hole in the graph. So I'm going to put a solution, okay? 1, 2, 3, 4, 5, solution. Well, I'm going to start with factoring numerator and denominator. In numerator, 2x is factored and x minus 1 in parentheses. Denominator, using the formula x minus 1, x plus 1. I'm going to cancel x minus 1 and have 2x over x plus 1, which can be represented as 2 doing division. 2x, x plus 1, it's 2, 2x plus 2, minus 2, minus 2, x plus 1. So what I have, 2 units up, 1 unit to the left. Sorry, not x, but 1 unit to the left. And this minus is going to do reflection, right? Reflected. About x axis. And because I canceled x minus 1, x is not equal to 1 because it's turning it into 0. It's going to give me a whole. Oh, now I'm ready to graph. So first, 2 units up. Horizontal asymptote y equals 2, horizontal asymptote. 1 unit to the left, x equals 1, vertical asymptote. And my graph is going to be reflected from normal graph going in the first and the second, third quadrant, and this one is going to be something like this, right? And x equals 1 is going to make a whole. X equals 1 is over here. It's 1, right? And I'm going to put a hole here. That's how my graph is going to look. That's y over here, that's x over here, that's 2, that's minus 1. Okay. Okay. The last thing in this section I want to talk is a slant asymptote. For slant asymptotes, you just need to know like what they are. I don't think that we are going to have very complicated problems about them. So slant asymptotes. Well, let's go back to functions where the power of numerator is greater than the power of denominator. If you remember the rule was telling us that we cannot find any horizontal asymptote in this case. You see, for example, this is cube and, oh no, sorry, that's a square actually. This is a square and that's the first power. So because 2 is greater than 1, no horizontal asymptote. But I still want to kind of do division. X squared minus 3x minus 1, x minus 3. So first I multiply by x squared minus 3x. Then I bring minus 1 down. Oh, it was plus 1 actually. Sorry. Plus 1. I did not copy it correctly from the book, I guess. This problem. So it's plus 1. Well, what I'm going to do, guys, I'm going to write down f of x as a result. So I have x plus 1 over x minus 3. Well, I see that at infinity, when x goes to infinity, this will go to 0, 0. But this will go to infinity. So there is no horizontal asymptote. F of x is not becoming any constant line, but it's becoming a line y equals x. Y goes to line y equals x. Well, this is called a slant asymptote because it's a still a straight line. Slant asymptote, it's a horizontal line. Y equals mx plus b. Not horizontal, but inclined line, actually. That's slant. Well, let me graph the function. I'm not going to consider any, like ask you to solve any examples, but that's how we find the slant asymptotes. First, my vertical asymptote is x equals 3, right? How do I graph slant asymptote? Or just y equals x. So my graph at infinity is going to look like x. So that's what is going to happen to my graph. So normal graph will approach actually x-axis, right? But this graph is going to approach actually y equals x line. This is called slant asymptote. Well, if you do 1 or 2 problems in the homework on slant asymptotes, that's going to be great. Okay, I think we are done finally with 3.6.